Okay. So I was trying to understand the grounds of Fresnel-Huygens principle, but I will stick to the validation of it, which is which is basically an integral, which the equation, the equivalence of the integral. We'll see that. We'll construct it somehow. We'll do that, and this is okay. This is Fresnel-Huygens. This is Fresnel-Huygens principle, and its validation. Okay. So the main thing I'm referring to is basically the whole understanding is adopted from Max Born and M.R. Wolf principles of optics. Okay. So So the basic thing, what a Fresnel-Huygens principle says is you have a light source and you have spherical waves, right? It basically emits spherical waves. That's the basic thing, right? The first thing is that spherical waves are the basic ones. Everything emits spherical waves. This point source, let's call it P0, and let's say this is P. So we have some points, right? Let's consider this point Q. So say this is R0 and this is S, this is B. Again, I'm just going on with the notation given in the book, right? It's called B. So this Q emits a secondary wavelet, okay? Acts as a secondary wavelet, Cool. So how this is gonna look, I'm gonna make this here, perhaps resize it, put it here, and this other. So how is this gonna look like? According to Fresnel says this, like, this is an approximation, right? This works to some extent, and I should point out here that I'm in like semester 3 now, and this is classical optics. It's the basic linear optics we're studying now, like the works of Fresnel, the initial works of Fresnel perhaps. And we are gonna lay some assumptions here. Assumptions in the sense the approximations and the empirical, the formulations. They are reasonable, I guess. One is that the wavelets, the spheres of wavelets, the spheres from wavelets limit to an arc angle of pi. Limit to pi. into 180 degrees, that is pi. So how's this gonna look like? So basically, draw a tangent here. Such that these are the secondary wavelengths. Okay. Now one of these is going to land here. Somewhere here, right? Okay, this is bad. Okay. Somewhere over here, this is gonna land. Let's say here. Like this. Okay. One of its wavefront is gonna land here. Yeah. That is it. It is limited to 180 degrees. So we can immediately see that not all regions of this sphere, this spherical wave is not going to contribute. To the field at E. Okay, why is it? We can attribute this directly to first assumption or rather Fresnel's hypothesis, something like that. It works. We shall see in later classes, of course, what are the grounds of even these, right? Maybe they are photonic, quantum mechanical things, right? Let's see. But this is how classically we explain it. Explain the results classically. That's what we do here. So yeah, let's see. And there are some interesting results and integrals over here, right? So yeah, you can immediately see that there will be a limiting factor for this. Like, see, we draw a sphere. Okay, we draw this is a point P naught, and if you see that there is a tangent which is which is coming from P, right? This is Q, and this is going to be 90 degrees, right? So the wavelet is going to get limited. I mean, it's something like it kind of makes sense, but it does not. That let's say there's a vector K here. K doesn't have any component along P. It's naively saying that. I don't know. It is not even saying that maybe, but it kind of looks like that, feels like that. Let it be. I just put it that way. Yeah. So where will the how will the wavelets be? This is the limiting case, right? Okay. It is like saying approximately 0. Okay. We term this the field due to this is kinda 0. I don't know. It is maybe equal to 0. Let's say we're gonna represent this mathematically further, of course. Let's see that as well. Yeah. So basically, on these lines, what Fresnel's formulation gives us is, of course, along with Huygens wavefront hypothesis. Okay, theory. Huygens wavefront works, those things, what we get is u at p is equals to, okay, let's say this, u of p, this is r naught, right? This is v again, this is s, and we are being limited to this. Yeah, this. We need this area, this volume, this area of wavelets, secondary wavelets, give a field at P. Okay, this is that surface, this surface. Okay, so u of p, due to one such element, you see, yeah, there's a symmetry here. There's a symmetry here. What symmetry is that? We are kind of already. Let's discuss this symmetry here, and let's put this on a hold. So what we are doing now is, what we would like to see is that there is a symmetry. Before that, the inclination, you see this 90 degrees factor, right? This 90 degrees factor plays a crucial role here. Fresnel says that the inclination factor k of chi, okay, where chi is the angle that we discussed here. This here this and this is chi. This is chi, right? This point connecting here and a normal over here. This is chi. Okay, the wavelets, they are here like this, and the chi is like this. This angle is chi. Fresnel says that it depends, the field depends on inclination. Okay, field depends on inclination. Okay, cool. Now we see that there is a symmetry. With respect to chi, that is k of chi. So what is it? Simply this thing, right? So there is a surface, there is a infinitesimal area. Okay, this has same chi. Now this has same chi all over here. This is a 3D figure, a cone. So you see a cone of similar chi's. Cool, right? So to evaluate, so yeah, let us revise things now. First thing is that there exists only a part of the spherical wavefront influencing the field at P, there exists only a part of spherical wavefront originated from P naught, of course, influencing the field at P. Cool. Now we further see that there exists some set of regions influencing in similar, that is same amounts, which is given by k of chi, their inclination factor chi. They have same chi, have same values of chi. Now, okay, these are the things now. Now we shall construct a formalism which we have been holding on to. Okay, Fresnel's formulation of this. Okay, we can set this wavy thing when Fresnel added few this mathematical rigidity to it, and here's what we get. U of P, due to one such contribution of chi, one similar chi, is equals to the inclination factor times the amplitude at Q, which is this. This is the amplitude, this is the amplitude secondary, this is the amplitude times a spherical nature of these, showing an effect at P. Now times there is an area factor. Area factor, right? Okay, let's see this. This is a spherical wave characteristic. This is an inclination factor. And this is an area factor. I would like to see this as a number of aperture-ish things, right? Number of not aperture, sorry, I'm jumping steps, sorry. Number of secondary wavelets. Of course, right? Because it's not just one emitting, it's the whole area emitting, right? This whole a strip of thing which has this thing, this inclination chi. This is P. Okay, cool. Now what we would like to see, we would like to prove the Fresnel-Huygens principle, which says that basically holds pure the wavelet of the primary wavelet. Every point on primary wavelet behaves as primary wavelet behaves as a secondary wavelet which itself assumes a characteristic you can see that assume a characteristic spherical spherical propagation. This will not be happening. This is just treatment of it like that way. If we never know what happens, it's just formula. Like we develop a formalism to explain. Yeah, I mean it can be what it is. But yeah, still. Okay. Yeah, what does this characteristic mean? Characteristic mean this is chi, and mainly this, because ds is obvious, because there is an area of secondary wavelets. We shall multiply it with it. So that is an essential factor. And amplitude, it forms a basic of spherical propagation. The amplitude at that point, at q. Okay, this was just the basic. The main things come ahead, which is so the final field at P, is equals to the inclination factor k chi integral a e power minus I k r naught by r naught times e power minus I k s by s ds. Integrate over the s. Okay, this is the field. At P due to what do you say? Due to I don't know, maybe I'll just say I. Okay, something is fishy here. This is for a chi and for one point. We shall integrate this exactly. We shall not put it just now. Okay, yeah. We shall sum this over the surface. That is when this integral comes, right? Yeah. So this is the thing, and let me just look at what exactly it is. It was I don't know if I can put this here. So basically it was this. Okay, let's write ds. There is a factor ds indeed. There is a factor ds of confidence myself wrong. This is the elemental thing. Acha. Okay. Got it. Yeah. I get it now. Yeah. This is due to us. Due to the whole thing. Whatever I was discussing back then. This was the whole thing. This was ds. Now you integrate over ds. You get it. Integrate over ds. Okay. Integrate over ds over s with respect to ds. We cover all the secondary wavelets influencing the field at B. Fancy F1. Okay, now what should we see now? That is it. That is the field. This is the field now. But you see, the original light source in that spherical wave, it also has some characteristics, and it also gives field at P. Field at P is simply A times e power minus ik. Let's say this is B. Here I said that ik R0 plus B or R0 plus B. This is the field at P. It is as simple as that. Now we would like to see how the wavefront, the secondary wavefront hypothesis, validates and holds and is consistent with this. Cool. So I'll write again here, UP is K chi. Actually, then chi shall be inside, of course. Yeah, chi should be inside. So I will put this here, put this here, put this here. Cool. Which is okay. One thing is not necessary is this. This is a constant. This not by R0 is amplitude factor. We shall integrate over S. The things are IKS by S times K chi. I don't know how to write this chi times ds. Nice. We have some things to calculate here. We have kx to calculate, dx to calculate. One thing is that ds is basically r0 square sin square theta d theta and d phi. This can be thought of as a sphere with this band. This is this elemental area. Okay, this is given by the polar tilt. This is the polar tilt. I call it polar tilt. And this how do I say it? I mean, this turn, right? This turn around this curvish part, exactly. This curvish part is given by the azimuthal angle, which is consistency, which is this phi, and a projection of this over xy plane. Sorry, I suck. So over xy plane, and this is an xy vector, which is r sin theta, and this is azimuthal angle, and this becomes azimuthal tilt, right? A tilt like this, a tilt, okay, this is fine. A tilt in the plane in this direction, or tilt in inclination thing d theta and d phi. This is r sin theta, this is our d theta. So d phi. Yeah, basically, yeah. The length is that. This length is r. Yeah, this is our sin theta d phi. Something like that. Yeah. Okay. Now. Look at it. We're trying to integrate this. This is straightforward. This we shall calculate. This is here. We'll substitute this over there. And I need to look at the treatment. Okay, yes. Okay. Okay. Here comes the physical part. I mean, the way this whole integral is a weird thing. They call it zone construction. I mean, yeah, we just construct zones, of course. That is clear by Fresnel. Okay, so basically this is constructing node P. This is R node. It's constructing some spheres, resulting in different zones and so on, and that the yeah, what do you call it, the edges of that, these lie at b plus lambda by 2, p plus 3 lambda by 2, 5 lambda by 2, and so on. Did what? Okay, yeah. So 2 and 3, yeah, and so on. Yeah, that is it. That is the story so far. Yeah. So he proceeds by constructing the zones. Why does he construct, you see? You can see where this leads to. You see, you can assume each zone as a door box area. I don't know, maybe a door box, something like that. I mean, you know, the integral of small stuff or small elements, something like that, maybe. Yeah, each zone as an element contributing to P. So we will write one thing is straightforward, which is cosine rule. The triangle P naught Q S theta and R naught and P we apply cosine rule to get s square equals r naught square plus b square minus 2 r naught b cos theta. 2s ds equals to 2 b sin theta d theta. Wait, what? I just need to have this over here. Yeah, I just don't remember stuff yet. Acha. Oh damn. My bad. It's r naught plus b. And here, okay. And here from cosine rule, we have s square is equals to r naught square plus r naught plus b whole square minus 2 r naught plus b cos theta. So, which yields 2s ds is equals to r naught plus b sin theta d theta, which is plus. Okay, now we shall put that in this to yield ds is equals which was basically, what is it, r naught square sin square theta, now sin theta d theta d phi equals to r naught square sin theta d theta is s ds. What's s now? Well, just refer 1 minute. I see. Okay. And the d theta is s ds by r naught plus p times r naught times d phi. This is important for us, of course, this too. We've just converted ds into d small s and d phi, which has no dependency from the side of integral. So it will be a simple integration, which is to be fine. So we achieve integral s into r naught s ds by r naught plus b into d phi. This is gone, and there is a k chi, sorry. What shall we do with that? Exactly. One thing which is discussed in the book is not going to be larger than wavelength. That's fine. It's just that the zones are small enough. And stuff. But yeah. Okay. Now we shall, of course, we need to evaluate the k chi 2, but we are integrating zone by zone. Zone by zone. So, uh, so the contribution of jth zone to UP is so we are trying to do something like U of P, and I'm trying to understand this stuff basically. U of P equals at J due to jth zone. So due to jth zone is equals I understand that he is integrating it. Okay, sorry. My PC server. Yeah, that's good. That should be good. Nice. Yeah, that's nice. That's nice. It's doing good. Okay, so the design, but S is again different. This is different. I mean, yeah, I mean, this is interesting result, but this is, oh my god. Let me see. So we constructed some zones over there. Let's see. Constructed some zones. Each thing is lambda by 2. Okay. By 2 is small enough with respect to R0 and B. Okay. Now, I want to see how the recording is going on. Oh, 44 minutes. Oh my god. I think I'll stop it and continue with the next part. I don't know. Maybe I'll just see this dominance. Let me see it. U of jp equals 2 pi a e power I k n plus b. Okay. K k j e I. Okay. So contributions of that zone to U of P is. I mean, why is he integrating? The S's we need to integrate over all the stuff from. Wait, what? This is the polar angle here. This will be phi here. Now we are taking this part, right? This part. So what should be varied here? Is it r sin theta d theta or a phi? R square sin theta d theta d phi. This is fishy. Well, wherever it is. Phi is not rotating 2 pi, by the way. it all depends on that, but theta is here. Oh, okay. So this will be our ideal z-axis now. So twist it. So yeah, just twist the whole thing and look from other side. And where will that fall? This, and there should be a x-axis somewhere. X cross y is z. Why don't I take another pen? Somewhere around this color. This is y. This is x. Yeah. This is z, and we are measuring theta here. So the phi falls over here. So what is our azimuthal angle now? Azimuthal angle. Let's see this now. Now you are. Yeah. This thing is similar to this thing. This thing over here. This thing over here, right? The z, the x, the y. Cool. So yeah, we can write like that. It's fine. Okay, that is for one thing. Now we are rotating phi to pi, so it covers only one zone now. Each zone has its different area, different s, and you are integrating s from here to here. I mean, what the hell? Where is s? S is this. And you are constructing a zones. With centers at P, we construct zones. Acha, wait. No, not what I was thinking. Okay. Okay, we construct zones and we put it over here. And I don't understand why is he integrating s. Acha, what the heck? No. And no. This will be a circle. This will be a sphere. This will be a circle. This will be a sphere. If you are saying like s and this b plus whatever j lambda by 2, these are equal, then it is very, very shitty. You're saying R0 is big enough and B is big enough. R0 is big enough. R0 is big enough, then yeah, then ideally you get a plane wave like this. Well. Okay. No, man. Come on. No. What you're saying here is you have this S. Yeah. What if this is bigger? This is bigger and bigger. Exactly. No. It becomes more shittier. I'm getting some ideas here, but going towards plane wave. No. It's gonna happen. I need to figure this out. Okay. mm, I don't know. I mean, okay, let's see this. Plane waves fall like this. You're saying S is like this. So what does it mean? All the particles will be acting like this. Then I mean, it's plane waves. So more the tangent will be higher and higher. The zone will be more zones will be there. No problem. That's not a problem. Now, what about this radius? Can we neglect this? Now these are going to microscopic things like relative to lambda, relative to relative to r naught, relative to b r naught. R naught is bigger, so that means it's plane wave, and we are considering at a higher distances. See, diffraction. Plane waves are incident. Here, this distance is higher. What happens now is that, see, it's far field thing. You see that? Far field things. Fresnel-Huygens is applicable for far field, something like that. Wiki page. Okay. Anyways, this is and what about this radius? This radius will it be smaller? We go higher and higher. What happens to this? How do you think that radius is there? If you take like this, then it kind of like disappears that. Yeah, you can see this mathematically. No problem. Let's take a sphere. Let's take this. What's this? This is theta. Let's say theta. This is r. This is r sin theta. This is the radius now. As r increases, this radius also increases, and my charging is down. Okay. As r increases, r sin theta increases at same theta. R sin theta increases, which means it's very higher radius, so it remains close to it. Right? So you do that approximation IKS by S, and you just apply the limits from okay, that okay. Now we have made S in terms of the limits of S as in terms of B plus the zone limits, right? Zone boundaries. Now the zone boundaries are B plus lambda, J lambda by 2, which means that J minus 1 and J are the adjacent things. And why are you integrating with in the adjacent things? In the adjacent zone, you get only one zone. I see. In between, yeah, he's just proving the point that any two zones provide kinda similar thing. I see. You see, it doesn't matter now. it doesn't matter because you have approximated to b plus by 2. Now you're reading it at j now. That's fine. Okay, that's cool. And this should be technically be charged some, but nice. Charging my pad. Okay. So what I understand is this. He has constructed zones for a reason, dude. These zones are cool. Okay. P naught. You construct spheres with center here. Nice. Okay, these are different zones. Now, remember one point. We are taking R0 to be higher, B to be higher, R0 to be higher. See, it can be due to experimental reasons, or experimentally reasons in the sense they thought this, they observed that these things work there. Okay, that's one point of view, and the second point of view is that theoretically, this is also practically. Practically for R0 B comma lambda, for reasonable R0 comma B, it does hold. But where does the picture of lambda comes in here? You don't need lambda to see that plane waves are. You see there. That's what was the drawing here. Yeah. In plane waves, like for reasonably bigger R naughts, the S, if B is longer, the change in S can be neglected, and also R naught, the radii is so high that the R sine theta R increases, radius is very high that it almost remains same with respect to the distance B. Okay, this is minimized and this is increased, so that's set up R0 comma B. This holds for lambda, so are reasonably greater than lambda. Actually, I see. They need to be greater though. But reasonably greater than lambda should suffice. Now this is more microscopic view, and I shall look at it at some point. Okay, cool. I want to look at a microscopic dig at R0 comma B should be greater, yes, but greater than lambda should suffice. One day perhaps. This is a question to look at. Okay, that is bad. So u of p was basically, let me revise my thoughts here. U of p was of course the amplitude factor times integral of k chi minus IKS by S ds. ds can be written as r square sin theta d theta d phi, which was written as r naught s by r naught plus b times ds times d phi. Now these s cancel out, r naught goes out, it's fine, and we have this things. We have now integral of d phi, it's basically 2 pi, right? This things, and the phi is in this axis, this is z, this is phi, yeah, this is phi, and phi ranges from 2 pi so that it can cover whole thing. 2 pi, cool. This is for a zone, yeah. We are calculating for a zone, no, for a Darboux zone, let's call it a Darboux zone. For each zone we shall calculate, we shall evaluate because chi varies, right? We shall analyze it somehow. You will see that, which is a times e power minus I k r naught by r naught plus b times k j for jth zone. In arbitrary zone, we shall see that the integral does not matter. For one zone, b plus j minus 1 lambda by 2 to b plus j lambda by 2. It's the distance from p, and we already have seen that if this is large, this s thing kinda remains same. So we just take this length as this length. Fine, cool. Times for one zone, for any jth zone, we have minus IKS ds over the zone by 2 to any two adjacent zone boundaries, two adjacent zones, two adjacent zones. Okay, that's the thing which will be evaluated something. Okay, we will do that, no problem with that, of course. Okay, it depends on j, of course it depends on j, I mean, yeah, it's some arbitrary j, right? It's still good. Yeah, 2 pi, I missed 2 pi factor of the integral of d phi. We shall do it over 0 to 2 pi, and yeah, we just evaluate this. Up due to jth zone is minus I k r naught. Okay, right. Up due to jth zone is equals to a k r naught by r naught plus b 2 pi k j x chi. This is s by l k psi ik. Okay, and I saw something fishy limits, fishy result here. Something fishy. What did he do? Well, he did nothing. He did nothing. Wait, what? Acha, he did nothing. Yeah. It's fine, it's fine. We shall just manipulate here. Okay, let's say this whole thing is C or C. I don't know. C. No, don't like it. Comma. Yeah, delta. I like delta. Delta times ik. E power minus ik b plus j lambda by 2 minus e power plus j minus 1 lambda by 2. Okay, we just take common. Take things common. So ik b j lambda by 2. These are common. 1 minus e power minus lambda by 2. What the heck? Well, and well. Of course, there is an ik always. Over minus minus ik lambda by 2. Okay. Don't forget the thing that k lambda by 2 will be pi. Because k is of course 2 pi by lambda. So this turns out delta by ik to e power minus ib pi times 1 minus I pi. What? Of course, e power I pi is something good, but something's fishy. Yeah, I missed j, of course. Okay, I see. This is legit. E power minus I pi j I pi. E power minus I pi is 1. No, it's 2, of course. Our legendary e power I pi, e power plus minus I pi plus minus 1. This thing over here. So this is delta by ik minus delta by ik 2 perhaps minus 1 power j. J plus 1? What? Okay, it's cool. No, it's not cool though. It's not cool. What? Okay, he did that. Where did minus come from now? What? From the beginning, he took IKR, not minus. That's fine, of course, because we still have the things. It's fine. We will still proceed to multiply by this to make things look good. 2I delta by k minus 1 power j. So, as of 2:42 AM, which is 26th Sunday 2021, I was able to prove that each the field to each zone of jth zone is equals to I by k if the pink sucks, to I by k delta is okay. We still have 4 pi. Okay. We will include this 4 pi I by k times equal minus I k r naught by r naught times our lovely chi times minus 1 power j. This is it. Okay, I understand. Oh man, this is good. Maybe this is it. Field at P due to jth zone. Next, we shall analyze it. For all j, that is up total is equals to summation over j up due to j. This is the thing, and it's end for this talk. Thank you.